All right, I think I'll start. So today's class is, this whatever this is just we'll be talking about how we have, the how we map scenes in the world to a camera. So basically, you have your, you can think of the world as just a collection of 3D points, and each 3D point has an RGB value. And this one, this what we're going to discuss today, it doesn't really we don't really concern ourselves with the RGB values. We're just looking at positions. So you have a 3D point in space, and it's got some position, and that position, it maps to some 2D location on an image. So we're going to talk about that today, and there's a few steps to this. I'll cover all of them. And so we'll start with this projection matrix, and this is nothing but, you just multiply a matrix to a 3D point and you get a 2D location. So let's look at what's happening in this matrix, right? So you have a scene and you have your camera, you have the location of all these points, you have the location of the camera, and you get an image based on these things. And all right, so yeah, this is basically the pipeline. So here's, you have a point and it's written in a homogeneous system, obviously. This point, it's represented according to some random, it's represented according to some coordinate system. So there's some arbitrary coordinate system in space, and you've written down the points according to that. And it's important you describe the location of everything with that. All right. And so even the camera location, it's going to be, represented using the same arbitrary coordinate system. So now you have these points, right? Let's just look at one point. OK, you do a transform and you bring it to the camera coordinate system. So now imagine you have, I'll explain why this is important. It becomes easier to map points from the camera coordinate system to the image. All right. And so the first step is just bringing it from the world system to a camera system. So now, you can imagine that your camera is the origin and all points in space are defined with respect to this camera. So initially, let's say my camera is somewhere, let's say it's at 111, right? According to some arbitrary some arbitrary constant, some arbitrary world coordinate system. And I have a point that's at 222. So just with respect to the camera, this point would be at 111. This is a very, very toy example. I've just subtracted 111 from it. I've made the camera coordinate system also. I've just aligned the camera coordinate system with the world coordinate system. All right. So this arbitrary coordinate system is what I'm calling the world coordinate system. All right. Now, once I have these points in the camera coordinate system, I'm going to project it onto an image plane. And from the image plane, I'm going to bring it to, into an array of pixels, basically what's being projected on your screen. Right. And that depends on, it's a device dependent thing. All right. So this is the basic outline. I have my point here. It's defined in some world coordinate system, and I bring it to the camera coordinate system, following which I bring it to a plane. And from that plane, I bring it, I map the locations as to where I displayed on my screen. And this depends on, your camera build and all of that. So we'll cover all of this. All right. There's this confusing figure. Just here's a few things. I'll show other figures that are easier to understand. So just leave this for now. All right. So this is the pipeline. You have your object to camera, and then camera to an image plane, image to sensor. And this is not really important. We generally tend to ignore this while teaching, but it's just done in the background. So you have all these distortions, your fisheye distortions and all these aberrations and stuff, and that usually the camera just takes care of it. So just, don't really worry about this, right? And so you have, okay, so this pipeline, there's two things. There's the extrinsics and the intrinsics. Extrinsics is about the external stuff. It's basically where the camera is. And intrinsics are about how the camera is built. So, all the focal length and all of that. That's gonna what do you say? That's gonna define how these points, after the image plane, how they come onto the sensor. So this just helps you get all the images into the camera coordinate system, after which we get them into the image plane, following which, there's some multiplication and also some operations done on this, and you get it into your on screen into something we'd like. Okay, are there any questions, or can I proceed? If there are no questions, then I will proceed.
Oh, quick question. Can you explain what are intrinsic and extrinsic parameters again?
All right, fine. So where did this go? Yeah, so the extrinsics. Okay, so again, I told you that the camera, its coordinate frame, it's described with respect to some arbitrary world frame. All right. So let's say I am sitting somewhere, and I'll just assume myself to be the the world frame, and I say that this camera is kept 111, 3 positions XYZ 111 away from me, right? And it's got some rotation as well. All right, so I'd say it's rotated 90 degrees above the x-axis. I'll explain all of this again, but just try to form a rough outline of what's happening. So I have some location description of where the camera is with respect to me, and I'll say that there's a point at 222. So I have some description of points and even the camera, the location of the points and location of camera and orientation of camera with respect to myself. But having it with respect to myself is not really useful, because I want an image from the point of view of a camera. So what I'm going to do is I'm going to set everything, I'm going to manipulate these values so everything is described from the point of view of a camera. So extrinsics parameters are basically just the external location of the camera. So it's like, where the camera is located and how it's oriented. Intrinsics are more about its focal length, its shear and stuff. There's some distortion and stuff that happens. I'll show you images of that, fisheye and barrel. So those parameters will, sort of correct the image. And the intrinsics also show you how points in the world frame, they come onto the image plane. All of this I'll just cover up ahead, but just think of it like this. Intrinsics define how the image is going to look, how the image is going to, define how the image is going to look from the point. I wouldn't say how it's going to look, how okay, extrinsics define the orientation of points and stuff, the viewpoint sort of thing, and intrinsics are more about, the minor corrections and stuff like that. That's one part of intrinsics though. So, if you have like a larger focal length and you have two cameras that are in two identical scenes, and one of them has a larger focal length than the other, the images are going to be different. So intrinsics are about that. I don't know if I've accurately answered, but I hope that clears something.
Yeah.
Is there any other?
No.
All right. Okay, your network is causing poor call quality. I don't know about that, if I'm cutting up or anything. I'll just proceed anyway. All right. So yeah. Okay. So let's do this. Yeah. This I just wanted to introduce the pipeline. So this is the pipeline, and I'll use another slide for what happens next. Let's see. All right. Fine. So yeah. Okay. So let's look at this. Okay, so for now, assume that everything is already in the point of view of of the camera, right? So I'll assume that this is my world coordinate system. Guys, can you see my cursor? Can you see my cursor?
No.
All right, you see the C point here, right?
The camera center?
Yeah, the camera center. Yeah, so just assume that the camera center is, is the global origin. So it's like the 000 of everything, right? And everything that's defined is with respect to this. So if I have some point X and it's got a value of 333, it's literally 333, distance away from this. Like it's defined as 3 units on the Z-axis, 3 units on the X-axis, and 3 units on the Y-axis away from this, right? So for just this part, consider everything to be in the camera coordinate system. But this is not ideally the case. Stuff is not usually like this. Everything is described arbitrarily. It's not arbitrary. It's according to some other world coordinate system. All right. So now um, we have this camera center, and assume that it's the world coordinate system, and you have some points over here. All right. So now this is a three-dimensional point, and you wanna get it as a two-dimensional point in this image plane. All right. So the image plane is f away from the center of the camera. In the pinhole camera, obviously the image is formed beyond the camera origin, and everything is flipped. But for the sake of mathematical ease, we're taking it. I don't know if Adil has introduced this, but we're just taking the just a minute. I'll just get a board and draw this figure. We're taking this. Just a minute, guys. Hi, can everyone hear me?
Could you stop screen sharing?
All right. Yeah, can you see the board?
Could you push back a bit?
There's nothing on the board yet.
Oh, okay. Fine.
Yeah, so if this point is the camera origin, and this is the point in the world, in a pinhole camera, the image is formed here where the film is here, right? This is your focal length. Is this visible?
Yep.
All right. So this is my focal length. This is my film, and the image is formed upside down over here, right? For mathematical ease, we're gonna derive all our images over here. It's the same length. These angles are similar, and this length is the same. So this line and this line has to be the same. So in a pinhole camera, the image is not actually formed over here. It's formed over here. But for all mathematical, for ease of deriving everything else, we're gonna stick to convention over here. Is this clear? Like, can I continue?
Okay.
Okay, cool. If you have any doubts, please just ask. All right. Can you guys see my screen? Can you see my screen?
No, not yet. Not yet.
I'm sharing my screen. I don't know. Yeah, is my screen available? Can you guys see it?
Yeah.
Yep.
Okay, cool. So yeah, again, the image, this is just a technicality. The image is not actually formed here. It's formed behind the camera center and it's upside down. But you know, it's the same length, and it's easier to work with stuff like this. So, right. So the image plane is, you know, it's a plane that's parallel to the y-x plane, and it's you know, f length away from the center. It's basically the focal length away from the center, right? So that's the image plane, and everything that's, you know, is projected on the image plane, that's going to be your image, right? So you have a point, and it projects onto the image plane, and we basically get a location of that point on the image plane. So you can use similarity over here, you know, this point. So the x, just look at it in the y. What do you say? In the so okay, so z is not counted anymore because it's just parallel to the xy plane. All points are gonna have a value of f. The z value of all points on this plane is just gonna be f. So we are just interested in the x and y part of it, right? So every x on this, you know, so according to this figure, every y, you know, every y location of a point is just gonna be y equal to f into y by z. And it's not very difficult to see if you look at this small f. Is there any way I can draw on this? Just a minute, guys. All right, fine. I'll just try to make do with this. All right. So this, if you look at these two triangles, C, capital P, and this point above capital P, and let's just call it small p, or let's just call it y prime, right? And you look at these other triangles, C, capital Z, and capital Y. This is the point, you know, that's at the other end of the blue line in this second figure. I can't highlight it or anything. Yeah. All right. So these two triangles, they're similar. So obviously capital Y by capital Z is gonna be y dash by f, and you can just rearrange and you get the value of y dash as the focal length into capital Y by capital Z, and you can extrapolate this to the x dimension also. So you get these xy locations, and these are nothing but the image locations in this image plane. So it's the projection of these world points in the image plane. Okay, this is a little confusing without, you know, highlighting what exactly I want to highlight. So I'm sure you have questions. Please ask away. I'll try to clarify them. Are there any questions, or is everyone clear? Okay, there don't seem to be any questions. Okay, so now we have a you know, a homogeneous coordinate. I mean, these points are represented as 4-dimensional points. This one is just a scaling factor, right? And we want to go into planar location, but that's also going to be a homogeneous thing. So we're going to stick to 3 dimensions. So we do a matrix multiplication, and we get this. So if you multiply this matrix, you'll get a 3/4. You'll get a 3/1 matrix, and this capital X is nothing but x by w. And if you write it down, you'll actually get, you know, you'll get this equation over here, x equal to fx by z. So just work out this example. It's a pretty neat trick, just converting this just converting this homogeneous coordinate into an image plane coordinate. So again, this is 2-dimensional. It's on the image plane. You know, at this point P, just above this point P, there's a plane. So these points are just points on the plane, and these points are the world points. and you do this matrix multiplication, and you'll get points on the plane. I don't know if everyone's getting this, or am I clear enough? Anything? Are there any doubts?
What is W there?
All right, so W is, okay, in this case, W would be nothing but Z, but in homogeneous coordinates, we usually write W as the scaling factor. So this is actually equal to X by W, and the second part would be Y by W, and the third thing would be 1. So that's how homogeneous coordinates are defined. You can divide the whole thing by the last element, right? So for 4-dimensional homogeneous coordinates, is this whole thing, this 4-dimensional homogeneous coordinate is equivalent to, something like 2x, 2i, 2z, and 2 at the end. So it's the same thing. Similarly, for this, it's a 3-dimensional homogeneous coordinate. So this whole thing is actually similar to something like x by w, y by w, and 1, right? So W is just like a inverse scaling factor. You divide everything by W, and that's going to be your location. So if you divide everything by W, in this case, W is nothing but Z. You're going to get, for this value, you're going to get Fx. For this value, you're going to get Fy. And for W, you're going to get Z. So when you divide it, you'll get, Fx by Z, which is nothing but this transformation. So here, this highlighted thing, x equal to fx by z, is converting this x in the camera coordinate system. This x is the location, is the x value of a point in the camera coordinate system, and it's it's being converted. It's just a linear conversion to something in the image plane. So doing it individually obviously was not really computationally effective. You can just apply this, this matrix multiplication, and you go from this 4-dimensional thing to this 3-dimensional thing.
Okay.
Is that all right? Are there any questions? I can't see. Cool. Okay, so I'll just go on with the next thing then, right? So this is all right, fine. So this is a projection matrix, right? It's called P, and we apply P to our points, and we get the points in the image plane. So it's this equation Px. All right, that's the projection matrix, right? And I explained the pinhole model wherein you're using the image is coming in front of the camera. This is not actually happening. It's just mathematically easier to work this way. The image is still being formed behind the camera center. The film is behind the pinhole point, and it's still upside down. According to this, the image would be upright, but that's not the case. This is just for maths. This is not what's happening physically. All right, the image is going to be inverted, and it's going to be like, it's going to be behind the camera center. But just for our sake, just for making things easier, we put it in front of the camera, and it's still upright. Cool. Okay, guys. So now, right. So everything's not really gonna be okay. Fine. I'll actually explain this first. All right. So now you have your P, which is nothing but F1 and this row of zeros, right? And so this is gonna be your camera intrinsics. There's more values here actually, but we'll come to that later. And for now, just think of it like the focal lengths are here. And okay, so this thing I0 is nothing but a 3x3 identity matrix concatenated with the vector of 0, a 3 vector 0, right? So this is a 3-dimensional 3x3 matrix. This I0 is a 3x4 thing, and this XC is a point in our camera coordinate system. I'm reiterating, these points are still defined with respect to the camera coordinate. So if you have a camera and I say that this camera is at 0, 0, then whatever value I say for the point, it's defined with respect to the camera coordinate. All right. So they've just broken down this P into this thing where K is your camera intrinsics and I0 for the time being, we write I0, but as the camera moves around, you'll have to change these values, right? So this is your camera coordinate and this is I0. Is this cool? Is this cool so far?
Could you repeat what you said about I0 once again?
Okay, so right now I have taken the assumption that these points XC, right, is always going to be in the camera coordinate system. That's not always true. They can be anywhere. So we can't always put I0. If this is not XC, then we can't put I0 over here, right? But if it is in the camera coordinate system, it's already defined with respect to the camera center. So we don't really need to translate or rotate or anything. So I'll get to that also. This operation basically helps convert the point into camera coordinates, and then we can work on it with our intrinsic matrix. This K is called the intrinsic matrix. It converts your points to where it'll be on the image plane. So if you have like two identical cameras and you have two different focal lengths, so if you have like a bigger focal length, the image is going to be bigger. So even though the location is the same, things can be different. Like with more focal length, they'll be more zoomed in. All right. Just have a look at these notes. The camera is at the origin. Z is the camera or optical axis, right? So this CZ is everything is along this line, and P is the principal. These are just small things. I don't think people really care. Focal length is in pixel units, and orthogonal image axis is. I don't know what this is. This is not important, I guess. All right, fine. So this is the basic camera equation. You have your projection matrix. It's decomposed into a matrix of intrinsics, and these are your extrinsics. So this I0 over here, because it's already in the camera system, we don't really need to translate and rotate and stuff. But these define your extrinsics. These depend on where the camera is located with respect to your world frame. And this intrinsics depends on the build of the camera. Is that cool? I'll continue, guys. Okay, there's a question. Will the transformation be the same for the inverted image? I don't exactly get your question. There's no transformation as such, right? There's no geometric transformation happening right now. So again, this image is the same as the inverted image. It's because of similar triangles. We saw that whatever is happening here is going to happen here. So the image is going to be exactly the same, except that it's going to be inverted from the original inverted image. So that inverting it twice just makes it upright. But whatever image you get here is what the image is going to be here, but just upside down. That's all. So whatever geometric transformation that you do is going to influence your original image, and obviously this image as well. Did I answer your question? Okay, cool. Okay, so that's the pinhole model. All right. Okay, so I'll detour a bit now. We'll cover this transformations, rotations, and translations. All right, and then we'll fuse these two and we'll get the entire camera equation. All right. So this is from a course that we had that you guys don't have, graphics course. All of this is useless. It's a nice little house. We don't need all of this. Right. So okay. So there's this notion of degrees of freedom, and I'll just tell it to you straight up. Rotation only has 3 degrees of freedom. So basically you can describe some rotation with using only 3 values, right? And with Cartesian, yeah, so if you specify. All right, okay, so anyway, okay, I'll get to that also later. This is 2 ways of representing 3D coordinates. Again, it's not really necessary. You have X, Y, Z, and you have polar coordinates and some length as well. So yeah, I mean, you can work out the math, and there's some math that happens here, some magic, and you can just do this. There's two ways of representing your points in space. It's not really important exactly, but all right. Okay, translating a point, you just add some value to it. So, you have a point 111. I want to translate it by, let's say, 110. So I just add 110 to that point, and now it's 221. So it's just moved somewhere in space along the direction of the vector that I added it. Right? It's just vector addition. That's all. That's all it is. Right? So it's some addition, right? And this is rotation. I'll explain rotation. So here's the thing. Let's look at 2D rotation first. Okay, so there's lots of ways to look at rotation. Let's look at this 2D rotation first, and then I'll show you another way of looking at rotations, right? So, okay, here's the thing. Now I have a point X over here, right? It's at some inclination alpha, and I apply some linear combination. I apply some linear operation on this, and I get these two new points, X dash and Y dash, right? So let's say that I want to rotate it by, and I want to get it at some angle theta, right? Rotate about the origin by theta. So this angle is theta. I don't know if you can see my cursor, but it's actually the angle between these two lines, the angle between the, this point 0 and the origin and xy, and the line origin and x dash y dash. So the angle between these 2 points is theta. And now we just want to rotate this about the origin by some theta, right? So you can just, work out the maths. I'll share this also. I mean, this is not the best way to look at it, but it's something like this, and you get this matrix. Guys, just give me a minute. Just a minute. Hello. Right. So I'll share these slides, and you can work out these derivations also. But it's not really important. But if you just look at it, it's just, you're converting this linear equation into this operation, right? Just this matrix multiplication, and you get this. And this is in 2D, but you can extend it to 3D as well, right? Rotations are orthonormal. I'll get to this as well. I'll just skip to the better way of looking at rotations. All right. You can just skip. You can, so this was rotation about the z-axis, and with 3D points, you have a 3x3. Okay. So again, we've just forget 4-dimensional homogeneous coordinates for now. Just look at everything as a 3-dimensional point in space, and this 3-dimensional point is what we're manipulating, right? So if I have a point, let's say 1, 0, 0, and I want to bring it to 0, 1, 0, then I'm going to rotate it by the z-axis by 90 degrees. Is that cool? So I have a point, just work out this example. I have a point 1, 0, 0, and I want to bring it to 0, 1, 0. And so to do this, I'm going to rotate that point by 90 degrees about the z-axis, right? So RZ of theta in this case is 90 degrees, comes out to be, just a minute, cos 90, 0, minus 1, 1, 0, 1. Right, so the matrix is 0, minus 1, 0, 1, 0, 0, 0, 0, 1. Right, the matrix should be something like this. Where is it? I think it's inverted. So if you just multiply this matrix to your points, then you're going to get 0, 1, 0. So if I do, if I multiply this by 1, 0, 0, I'll get 0, 1, 0. Right. So right. All right. So you can work out the rotations in the other axes also. Again, we don't really use these, but it's just fun to work these out. All right. One more thing. These are all working on three-dimensional points. We're not working in homogeneous. We're not working in homogeneous coordinates. So these are still three-dimensional points, and you're just applying these transformations. You're applying this, this to this three-dimensional point, and you're getting another three-dimensional point. That's all it is, right? Scaling is just, you have a diagonal matrix and you can scale any of your dimensions. So, a square could become a rectangle or something like that. Shearing is you have you have this not skew symmetric. You have this matrix, and you get sheared rectangles. Something like, let me just see an example. My internet's really slow, and we'll probably get a bunch of sheep because that's also shearing. Okay, that's not really relevant. Yeah, just a minute. Yeah, so something like this, right? Shear in X direction, shear in Y direction, and shear in both directions. Right, so it's something like this. It's again, all of this, we don't really focus on this. Oh, where did that go? Right. Again, reflection is not, you just reflect about some axis. Okay, so now this is what we care about. So everything so far except for translation is just a multiplication, and translation alone is just a vector addition. So we don't really want that. We want everything to be multiplication, and that's another reason why we introduced homogeneous coordinates, right? So now you have x, y, z, and 1. Your fourth column can just be another, can just be your translation vector. So yeah, so homogeneous coordinates in 2D, if you want x plus a, y plus b, then you can simply just, take the identity matrix in the first 2 by 2 block and an a, b vector in the last block. So again,
Hello.
Hello.
Yes, sir. What you just said, like, what is the reason why we introduced homogeneous coordinates?
Okay.
You said something.
Yeah, this is one reason. So translation so far is the only thing that we just need to add, right? Like
Yes.
in this example, if you have a point x and you wanna translate it, you're doing x plus t. But everything else, if you wanna say rotate it, you're doing some rx into this x point, right? So that's not really convenient. That's gonna incur some overhead, and that happens, so it's just a lot more convenient if everything is multiplication, right? So now you have your x, y, z, and another 1 at the end of it. So I have x, which is nothing but a homogeneous coordinate.
Okay.
So I can just the last column of my transformation matrix is gonna be my translation vector, right? Because it's just getting added to one.
But sir, isn't multiplication much more computationally expensive than addition?
So again, everything is multiplication, and switching. You're still doing the same number of operations, but let's say because modern computers are optimized to work with matrices better, this is a good reason to switch to multiplication.
Okay.
All right. So if I just write it as a block, just a minute. It's a block over here. Can you guys see this?
Yeah.
Let's see. Right. This is not the best way to go about this, but I cannot type latex on the spot. So I've just decomposed my transformation into this R is a 3 by 3 thing. This T is a 3 cross 1 thing. 0 is a 1 cross 3 thing, and 1 is just a 1 cross 1 thing. So this whole thing is a 4 cross 4 thing, right? X is a 3 cross 1 thing, and 1 is a 1 cross 1 thing. So this thing, just X and 1, is a 4 cross 1 thing. And when I multiply, I'm gonna get, so I've transformed my X according to some rotation, and I'm still just adding translation. And this is, so this right hand side is just one vector, and this top thing is a 3 cross 1 thing, and this bottom thing is a 1 cross 1 thing, right? But this whole thing is still one whole vector, the right hand side. It's a 4 cross 1 vector, and this is just the scaling factor, in this case 1. All right. Kanisha, have I answered your question?
Yeah, sir.
Okay, fine. Please don't call me sir. You can stick to Aryan. All right. So these are just some notes on homogeneous coordinates. This is again the thing about scaling that I was telling you. X, Y, Z. This is not equal to. Just think of it as I forgot the word, the formal word for it. And this is XZ, XY, XZ, and K, right? You just divide the whole thing by K. So you get X, Y, Z, and 1. I think Adil would have told you about this yesterday. X, Y, Z, 0 should be a point at infinity. Or rather, the plane at infinity. I'm not sure. Because dividing by 0 would give you infinite values. Right?
Yep.
Okay. So now, because we're working with homogeneous coordinates, because everything's 4-dimensional, again, we are going to concat these zeros and ones to our transformations, right? So these transformations in themselves are still 3 cross 3 matrices, right? And we're just adding this extra column just for the sake of so for the sake of dimensions, right? So this, if I just multiply this Rx theta into some homogeneous coordinates, it's still just rotation about x-axis by some theta. That's all it is, right? These are, you can just stack multiple of these matrices together and you get composite transformations, right? Don't worry about this. I will get to this. Okay, so translations are commutative because vector addition is commutative. This one seems fairly intuitive. Scaling is commutative. So okay, so for translations, if I translate by one, let's say I translate by 111 and then I translate by 010, versus if I translate by 010 first and then I translate by 111, I'm going to end up in the same place, right? Scaling is commutative. If I blow up something by 2 and then I blow it up by 4, it's going to be the same as if I blow it up by 4 and then I blow it up by 2, by a factor of 2. It's still going to be 8 times bigger in both cases, right? Are rotations commutative? No, they're not. And think about this, right? If you rotate 30 degrees about x-axis, let's say you are at you're at 100, right? If you rotate, okay, let's just make this an easy to work with example. If you rotate 90 degrees about the z-axis, you are at 100. All right. Everyone just try to visualize this with me. You are at 100 and you rotate about the z-axis by 90 degrees. So now you are at 010. Then you rotate about the x-axis by another 90 degrees. So now you are at 001. Let me just write this down. You first rotate about the z-axis by 90 degrees. So you end up at 010. Then you rotate about the x-axis, after which you end up at 001. Is that correct? I think it's correct. 00 minus, no, +1 only. So now if I switch these rotations, if I rotate about the x-axis first by 90 degrees, then I'm still gonna be at 100. And if I rotate about the z-axis, about the just a minute, guys. Okay, so if I rotate about the, okay, I am confused now. I have a point 100. I rotate about z-axis, I get 0 and 0. Then I rotate about x-axis, I get 0, 0, 1. If I rotate about the x-axis first, then I stay at 100, and then I rotate about the z-axis 90 degrees. Okay, all right, fine. I've got it. So I have a point 100. Just write this numerical down. I have a point 100. I rotate about the z-axis by 90 degrees. So I'll end up at 0, 1, 0. Are you guys following me? I have a point 100. I rotate about the z-axis by 90 degrees. So I end up at 0, 1, 0. And then I rotate about the x-axis another 90 degrees, and I end up at 0, 0, 1. So my first rotation was a rotation of 90 degrees around the z-axis. My second rotation was a rotation of 90 degrees around the x-axis. I started at 100 and I ended at 001. Now if I flip these rotations, I start at 100 again and I rotate about x 90 degrees. I'm still going to stay at 100 because my point is on the x-axis. So it's not going to go anywhere. And then I rotate by 90 degrees around the z-axis. It's going to go to 0, 1, 0, which is different from the point we ended up last time. So rotations are not commutative. All right. Translations are commutative, scaling is commutative, rotations are not commutative. Did you guys follow the example? Did that make sense? Let Casper teach too. Oh, right. Yeah, did you guys follow the example? Did that make sense? Anyone can just tell me, like, if you're having any doubts, please, I'll stop and I'll explain. Or if you have any doubts that you want to ask later on, just you can ask me later on as well. All right, fine, I'll just continue then. Fine. Okay, so now this brings in a lot of confusion. TR and RT, right? So TR is just let's say you have a translation and a rotation matrix and it's T into R into X. So X is first going to be multiplied by the rotation matrix, which means it's going to rotate first. And then it's going to be multiplied by the translation matrix, which means it's going to translate next, right? So if you do TR, you first rotate about the origin and you get this slanty arrow, and then you translate it. So you get this slanty arrow and it's translated in some direction. Now if I translate it first, I'd really like to point my cursor. If I translate it first, it's going to be at some distance from the origin. And then I rotate it, it's going to rotate like it's on the, like on a circle or something. How do I explain this? Again, let me bring out the whiteboard. I'll just draw, just a minute, just give me a minute, guys. right, so can you see? Yeah, so this is my original thing. I have, guys, is it visible?
Yes.
Is it understand? This is my arrow. I have the coordinate frame just sort of roughly drawn over here, right? This is just the roughly, this is the original thing, all right? So I'm gonna rotate it first, and if you can see, it's slightly bent, right? It's slightly bent.
Sir, it's not visible to me.
Okay. I don't know how to go about this then. Okay, I'll just is there any online paint? We try to draw that. I don't have an iPad like the rest of the guys, so that is a little difficult. Hi guys, can you see my screen? Oh, why is it so tiny? Okay, can you guys see my screen? Can you see this? Is my screen visible?
Yes.
Okay. Someone who could not see it, can you see it now? Kanish, can you see it now?
Yeah. Yes, sir.
Oh, fine. Okay. So now we have this weird arrow, right? This arrow is nothing but a collection of all points, and I'm gonna draw the coordinate frame in another color. Please excuse my amazing art skills, right? So let's look at this transformation first. Let's look at TR first, right? And all I'm doing is I'm multiplying these two matrices to this point, right? I mean, it's a collection of points, but it's multiplied to all points, so all of them they maintain their relative structure, right? It's just a collection of points that form this house-looking thing. So they're gonna stay the same. So when I multiply by R first, you know, R and X, let's say I get some T of X dash. Okay, it's not a J, it's a T. And this T of, and this X dash is nothing but, let's see, I have my coordinate frame. And it's nothing but just a bit rotated about the origin. Does this make sense? So I have translation, I have rotation, and I have my set of points. I rotate my set of points, I get a new set of points, and it's nothing but the original set of points just a little bit rotated. I still have this T left, right? So when I multiply by T, it's just gonna go in this direction of T. Let me switch. Oh, no, I don't want this. It comes here. And our entire thing moves like this. Does this make sense? Is this clear? Because this is a little bit important. If you're not understanding, let me know. I will explain it again, or we can take it up offline. Does anyone have any doubts? Please don't be hesitant. Anyone, anything? I think I'll proceed then. Where did it go? Let's look at RT. So again, I have my original figure, and I'm going to multiply this by R and T. Again, both R and T are matrices, right? So when I multiply this by T, this original thing by T, right? I'm just going to get a translated thing over here. Is that cool? So I've multiplied my set of points with T, and I get this translated thing over here. And now you must remember that all rotations happen about the origin, right? So originally this rotation was happening about the origin, so it was just bending a little over here. But now this rotation is going to happen about the origin and it's some distance away, right? So it's going to go in some path like this. Let me draw it with green. The path is going to take something like this, right? Is this visible to people? Are you guys understanding? I need some response key just to tell me if people are still in the class.
Yep, we can see it.
Right. So over here along this side is just T into R, and you get something like this. But if you take the other out, RT, you get something like this. So in a sense, basically TR not equal to RT. Cool. So whenever you see a transformation, whenever you see a set of transformations, let's say Rx or R2, R3, or actually I'll just type this down, wait. So you know, in practice, you'll see our transformations like, let's say, R1 into R2 into R3 into, let's say, X, right? So these set of points X, they're first transformed by R3, and you get X dash. Then X dash is transformed by R2, and you get X double dash. And X double dash is transformed by R1, and you get some X triple dash. So it's never just one point, it's a collection of points. And because all of those points are getting some translation, some transformation, they're all maintaining their relative structure. So when I'm doing this translation, I'm doing it on literally all these points. That's why they're sort of maintaining their relative structure. Obviously, you can't just multiply any matrix to a set of points and maintain its relative structure. These transformations are called affine transformations. They're line preserving. So straight lines remain straight lines, right? If you just multiply random matrices, it might not work out. I mean, it'll definitely not. It's not always going to be the case that you get the same image. You might get some weird random thing, but you just don't worry about that for now. Right. So again, this is not entirely important from what I'm supposed to cover today, but it's pretty intuitive anyways. So I'll just tell you. Let's say I want to rotate about this purple point, and I know it's at some vector C from the origin. So what I'm going to do is I'm going to translate it by minus C first, right? Then I'm going to rotate it, and then I'm going to translate it back to C. So if I just write this down in words, just a minute. If I have my rotation, let's say rotation C of theta, right? So guys, can you see this equation, the one I've highlighted? Is this visible, the highlighted equation?
Yeah, we can see it.
Okay, so what's happening here is, let's say I want to rotate about some point C, and the rotation I want to do is this R, right? If I directly apply R, it's going to rotate about the origin, and I don't want that. So what I'm going to do is I'm going to translate everything by minus C. So my points are now moved to the origin. All right. So this thing would give me, let's say, x dash, which is nothing but points at origin. All right. Then I'm going to take these points at origin and I'm going to multiply it with r. So now it's these points rotated at origin x dash. Cool. So I've taken those points over here. Where did that go? Right. So I've taken those points. Let's say I have this blue figure, and I move the entire thing to the origin. So this blue figure also moves with me to the middle, to around the origin. So this purple thing becomes sort of like new origin. Then you just rotate it. You rotate it about the purple point because it's at the origin now, and then you bring it back. Right. So when you get a rotated thing, it looks something like this. You do the same with scaling. Otherwise, it'll scale unevenly. So basically, about a point, you want to bring it back to the origin, do your transformation, and then bring it back. Right. You can work these out. This is similar to the thing we did over here. Operation on frames. I don't personally use this, and I don't want to teach you guys the wrong things, but with frames, the way of looking at, you know what, I'm gonna skip teaching you how to look at it with frames. I'm just gonna link some resources because I am not confident with this at all. So just have a look at this yourself. Some people find visualizing rotations with frames a lot easier than visualizing frames as transformations the way I was describing it. Points and frames in general. So you can just stack up composite transformations, right? So yeah, so you can just get, if you have transformation M, you can just stack it with transformation M2, M3, and you can do multiple things. All right, so okay. Now here's the thing. I'll close this. And it's 1 hour. Okay, I'll try to link rotation and translations back to our camera equation, right? So what we have now is, oh wait, I have a nice script for this. Can you guys see this? Guys, can you see this?
Yes.
I am not able to zoom into this. Okay, so here's the thing, right? This is my camera coordinate. This thing over here on the left. And this is my world coordinate system. And these are just a set of random points, right? And I have a purple point, I have a red point over here. So from the point of view of the camera, I should get something like this, and obviously scaled in. So I get this image on the right. Okay. So now my points, my camera is at some translation and some rotation from this original world point, original world coordinate system. All right. Forget the world points for now. This camera frame, it's at some weird orientation and away from the world coordinate system, right? So to describe the pose of the camera, let's assume that at first my camera is aligned with the world coordinate system. Just a minute, guys. Yeah. So at the start, assume that my camera is aligned with the world coordinate system, right? The X cam and X of the world are the same, Y camera and Y world is the same, Z camera and Z world is the same. All right. Then I apply some rotation. So it's all a little bit, it's all tangled up a little bit now. And then I apply some translation. So it's away from the world origin. So initially this camera frame is aligned exactly with the world frame. I apply some rotation, so it's in this weird orientation, and then I apply some translation, so it's away from, so the centers are away. Right? This equation is wrong. Don't look at it. So how do we model this? I have, let's say I have a set of points that make up my camera, and I apply rotation to all these points. Let's say I have some points X, okay, by describe I mean literally physically describe the camera. So you have, let's say you have just 8 points as a cuboid. That's your camera. I'll use the online paint again.
So I think you can use the board. Kanish says he can see it.
I can use the what?
The board. Kanish says that he can see it. I mean,
Yes, sir, I messaged you. Now I can see the board.
Okay, I didn't see this question. Just a minute. Oh, I didn't see this question. Just remind me if you're typing out over here. Okay. Jivitesh asks, you mean translations, affine transformations, right? Yeah, they are. They're all line preserving. So yeah, and they're all matrix multiplications. So yes, they are. Also, the origin here is the origin of the image plane. No, the image plane is away from the origin of the camera frame. So if I have my camera frame, let's say it's over here, right? This is the origin of the camera frame. The image frame is somewhere, it's at a distance from this camera frame, right? So here's my, let's say it's my, everything's along the Z axis. So this is my Z. Let's call this X and this Y. I hope I got the conventions right, right? So this is my origin, and let's say this is my camera frame, right? So the image plane is going to be at some focal length away from the origin of the camera frame. This is the principal point, is the origin of the image plane. But right now when I was teaching translations, you can forget all image planes and stuff for now. Guys, just a minute, 1 second. Sorry for the inconvenience. Yeah, where was I? Yeah, I was just explaining that the image plane is a little away from the, so it's away from the origin of the camera coordinate system, right? Wait. Okay, so Dipanvita, does that answer your question? Origin here is the origin of the image plane. It's not the same origin. Origin on the image plane, the intersection of the z-axis with the image plane is called the principal point, and it's not the same as your origin of the camera coordinate system, your camera frames. So all transformations are with respect to the camera frame origin. No, they're not. They're with respect to, okay, So okay, so we have 2 frames right now. Okay, just okay, hold your questions for 2 minutes. I'll try to clear this by drawing it out. All right. So I have, let's say, let's call this the world, right? All right, this is my world coordinate system, and my camera is located somewhere here, right? And I will call this okay. So now I'm going to define my camera by just 8 points. 1 minute. I'm going to define my camera with 8 points as this cuboid. Right. So my camera is this cuboid, and with respect to my, just with respect to my camera coordinate system, the camera points are described as 0, 0, 0. This is 1, 0, 0. This would be 1, 1, 0. If if this is X, this is Y camera, and this is Z camera, right? So this point here would be 1, 0, 0. This point here would be 1, 1, 0. And this 1, 1, 0, 1, 0, 0 is all with respect to the camera coordinate system, right? If this was some origin and I said 1, 1, 0, this would be the point, right? But this is respect to the camera origin, right? But what we usually have is we don't have everything in the camera coordinate system. We have everything in the world coordinate system. So it could be some arbitrary thing like 128, 2, 3, right? And obviously we're not going to define it in terms of those. We're going to define it in terms of transformations, right? So how do we achieve this? All right. So what we're going to do is just think of this. Okay, from a graphics perspective, from a computer perspective, you initialize your camera frame and your world frame together, right? They're both aligned, right? Is there any question? Origin is the camera center. Okay, so I'm answering these 2 questions right now. Jivitesh's and Dipanvita's question. Right. So originally, let's say that both of them are aligned absolutely perfectly, right? So this point is 1, 1, 0. It's the same in both frames. Now what I'm gonna do is I'm gonna apply some rotation. All right. Okay, and all these points X, right? All these points X, let's call them this collection of points X. I'm going to apply this rotation R, some arbitrary rotation R on all these points X. All right, let's extend this. Just a minute, guys. Let's see. So when we apply this transformation R, it's with respect to the world frame. And right now, both of them are the same. They're exactly the same. So when I apply this transformation R, what I'm going to get is my world frame is going to stay the same, right? But my camera frame and my camera points, they're going to orient a little differently now, right? I've rotated all these points. So just to get that in perspective. Right, so the whole thing is a little oriented a little differently now. So right, so what was originally 1, 0, 0 is now something else. Okay, this is the part where it gets confusing, and this will take time for you to understand. So it's still 1000. So it's still 100. If I look at it from a camera perspective, right? It's still 100 in the camera frame, but it's some new weird value in the world frame. Is that clear? It's still 100 if I treat my camera frame as the only frame that exists. But it's not the only frame that exists. There's another world frame also, and these two are not aligned the same. It's some weird number over here. Cool? Are there questions? Okay. So this is what's happening when I apply Rx, right? This is on all my points that describe the camera. I'm getting some weird orientation like this, right? And then I just translate this entire thing. So let's just a minute. Okay, so my world frame is still over here. It's still sitting there idly, but I've translated all my points in the camera frame. Is this cool? This is my camera, guys. This small black cuboid is my camera. And I've translated it also a little bit. Just a minute. I'll use a different color for translation. Let's see, purple. Right? I have translated it also by some T. So let's see. This 000 originally was 000, and 000 stayed 000 even after translation, even after rotation. And then when I translated it, it became some T. Right? There's some vector T, and that's how much all points have translated from the origin. So now I apply this rotation and translation to every point on this camera, or rather this frame. So the relative structure of this whole thing is still the same. So do you understand how applying R and T describe the location of the camera with respect to some arbitrary world frame? Guys, if you understand, please, I'll need some interaction now. If you're not understanding, just let me know. If you have questions, ask so I can know where I'm going wrong and where you guys are missing out. Okay, fine. Are the other people, do you have doubts? Because this builds up for multi-view geometry. This is relevant for the upcoming lectures, which I will not be taking. Okay, all right. So here's the thing now. You have these points, right? And they can be described in both the camera frame and the world frame. But what happens is we have, let's say, okay, I'll just start over now. Right? So here's what happens in real life. You have a nice little world frame sitting here. Okay, and you have some points that are described in the world frame. Right, everything in red is described in the world frame. So like this point here, let's say, has some value x over here, some value y, and some value z, right? All of these are just, you can think of them as vectors, and all of them have values that originate, that are based on this origin, this world origin. All right. Now I have a nice, I have a nice little camera over here, and I describe it with this equation R and T. All right, and this little camera is oriented something like this. Right. So my goal now is to convert these red points into green points. All right. The red points, they're all described with, with respect to the red thing. They're all their values are with respect to the red thing. And I want all their values with respect to the green thing. All right. The previous thing that I just explained, it was you had a camera, you rotated it first, and then you translated it. So can anyone build up as to where I'd go with next, as to how to get these red points into the green points? So we started with this green frame oriented exactly with the red frame, and we did some rotation and translation to get it into this position. And now I'm saying I want to get it back. So I rotated first and then translated. Could anyone tell me what I have to do next to bring it back? Yeah.
Do you have to do the inverse translation followed by inverse rotation?
Can you tell me what this would be? Just physically speaking. So I rotated first and then translated. Logically, I should translate it back and then rotate it like the inverse rotation. Oh, I skipped out on this because it didn't really seem relevant at the time. But your rotation matrices, they're orthogonal, which means that R inverse is nothing but R transpose. So this is a neat little thing. Computation is really easy for inverse translations, right? Just remember this. And yeah, it physically makes sense also if I had no translation, if I just rotated by some R to get it back to my original location, I would just have to multiply by R transpose. So here to get the green thing, in its position, I rotated first and then I translated. So what I'm going to do is I'm going to translate it back and then rotate it. I'm going to translate it back first because that's we want to rotate about the origin. Because if I do the inverse rotation about the origin, there's going to be some scaling factor here and it's going to go all haywire. Right? What did Harsha say? Someone couldn't hear him. He just said you have to do the inverse translation and inverse transformation. And I'm just explaining what that inverse transformation is. So to get our camera in its position, we multiplied, our, oh wait, let me stick to convention. Just a minute. Let's see. We multiplied X camera. We multiplied it by R and we added some T. So this got us to its location, right? I'm going to call this. Oh, wait, I made a mistake. You multiply and transform. See, everything was described in the camera was described in the camera's frame only. So I rotated that and I translated this. And now when I do that, I have the camera stuff in the world frame. And a way of writing this convention, usually you write it like this: X camera in with respect to the world. Cool. I wanna bring all these. So I have this, and I want to make all these red points back to green. Right? I want to make this X back to green. Or rather, I want to make this X camera with respect to world into the origin. And I'm not just going to multiply it by a zero matrix. That does not make sense because everything will just get squeezed to the origin. There's another way of doing it. All right. So how do I go about it? Let's see. What I'm going to do is I'm going to translate everything back first, right? So I have these points. I have these X. Let's say I have these X world points. And I'm going to translate everything back first. So writing translation as a matrix multiplication is nothing but this is my identity. This is 0. So minus t over here. And this is a 1. Guys, is this cool? Is this clear? All I'm doing is I'm translating everything back by what my camera was translated. Just give me a sign that you guys are listening or something. Got it. Okay, fine. So what happens now is you have this is my nice little world frame, and because everything is translated back, right? There's no rotation yet. There's just some translation, and I applied this translation to all these tiny little points also, so they're also translated a little bit back. Is that cool? Look at this. So what I'm doing is I'm aligning my camera frame with my world frame, and I'm getting all these points. I want to convert all these points so that they're green. So I'm manipulating their values, and geometrically it's the same as aligning my world frame to my camera frame. Cool. And then let's just say I apply the inverse rotation to this. All right. Let's call this. So I translated first. I have these X world points. I translated them. I mean, I did a negative translation, and I got this X dash W. And now I'm multiplying X dash W to R transpose, which is the inverse transpose of what we originally did to get this camera in this orientation. Right? So what we get is we get this is our world frame. This is our camera frame. It's absolutely aligned with the world frame. And now it doesn't matter what color I use because those points are again manipulated. They're moved around in such a way that their relative structure to the original camera frame is still the same. And because the camera frame and the world frame are aligned, whatever values I have is the value of these points in the camera frame. So these points are described in the camera frame. There's a lot to process in one lecture, but just try to just see the main point. If you have a camera that's so if you have a camera that's location is given by R and T, gives us the camera location, then we have to do first an inverse translation. So we multiply it by minus t. and then we do an inverse rotation. Is this cool? Yeah, guys?
Yes.
Okay, so this equation is wrong. This has to be R transpose and not just R. If your camera is given by R and C, if the rotation of the orientation and of the camera is given by R and C, which are your extrinsics which define the pose of the camera, if they're given by R and C, then getting your points in the camera frame, this should be R transpose. So deriving this is not really an issue. Your translation matrix is nothing but it's an I and it's a minus T. Over here it's a 0 and here it's a 1. So this I is a 3 cross 3, this minus T is a 3 cross 1, this 0 is a 1 cross 3, and this 1 is a 1 cross 1, right? Since we do translation first, our equation should look something like this, T into X world, right? This is what it looks like after translating. And I'm just going to write this as T dash, right? Or wait, let's just write this X dash. And X camera is nothing but my inverse rotation. That's all it is. 0, 0, 1. Right? So this R transpose is a 3 cross 3 thing. This is again a 3 cross 1 thing. This is a 1 cross 3 thing, and this is a 1 cross 1 thing. All right, and I'm just going to multiply this with X dash. So I finally get X camera equal to right, and over here I'm going to replace my X dash with T into X camera, sorry, X world. This is fine. This is bothering me. Right. Okay, so I have some points in X world. I have the orientation of my camera given by R and T. If I want to get it in the frame of the camera, I'm going to do this. I'm going to take R transpose and minus T. And basically when I multiply this, I'm going to get a matrix that looks something like this. This is the important thing. I want to convert my world points into my camera point, and this is the equation you have to look out for, right? So once I get my world points in my camera points, you can simply, you already know the projection matrix. Once I have my world points in camera points, I can just plug it in here, over here, and I get points in the image plane. So yeah, that's the situation. And getting it from image plane to your sensor plane, again, you just a minute. I'll not go in depth about that. Okay, it's nothing big. It's just your, what do you say, your K, it's just shifted by some constant, because it's just a your image plane is gonna have values from, let's say, minus V to plus V, and minus W to plus W, or rather this is W to minus W. But arrays start from 0, 0. So you basically shift the whole thing so that this point starts at 0, 0, and you can achieve that with this. There's some sharing stuff also, but we don't really look at that. And this is your general camera equation. I've just rushed through the last part, so I'm sorry about that, but I think I'm running short on time. And I'll take doubts now. Is there anything else I have to cover? No, there is nothing else I have to cover. There's only about 6 of you left anyways. So if you have doubts, please ask away. If there's something you didn't understand, just let me know in here or let me know somewhere else. I'll be uploading resources so you can go through those. There's a bunch of notes.
What exactly is the sensor plane?
Sensor plane is your camera. So now you have your, what do you say, from image, you've got everything nicely done. But okay, so in image plane, again, it's in your camera coordinate system only. It's a plane, right? I am rushing, just give me a minute. I will explain. This is my, for now, this is my camera coordinate plane, coordinate system, and this is my image plane, right? There is a image that's created over here. Okay, and just look at this carefully. This point over here is some minus X, some plus Y. This point over here is some minus X minus Y. This point over here is some plus X and minus Y. And this point over here is some X comma Y, right? Again, these are locations. They're not the RGB values. We're only looking at location mappings. And because your pictures and everything, they are arrays, right? You need to convert this discrete thing, sorry, this continuous thing into this discrete thing, and also take care of this 0, 0 thing. So the discretization is done with your focal length only. Your focal length is actually not in millimeters or something, it's in pixel values. So that's why you can have a different focal length for X and a different focal length for Y, and it's in pixel values. And there's a, so that part comes over here, Fx, Fy, and 1, right? And over here you have some scale, you have some translation factor. So I want to get this point to 0, 0, right? Because this is the first point in my image, and this is over here at 0, 0. So I'm going to translate it by X, or and bring this down by minus Y. So it comes all the way down and you have it in this one. If you don't do this, you'll only get like half the image. Like this is your entire image, but you'll only get this bottom right corner. So you bring it down so you get the whole image. Did that answer?
Yeah, I got it. Also, could you show the equation ones that you typed on? I mean, the equation for
Yeah.
rotation and translation.
Yeah. So this is the correct one with R transpose and minus T if R and T describe the pose of the camera.
The second one is minus R into T, right? The second element, as in the second matrix.
Yeah, yeah. It's minus R transpose. I'm sorry. R transpose T into T. Is this cool?
Yeah, okay.
T is a vector, a 3x1 vector.
Yeah, okay.
And R transpose T is also a 3x3 matrix.
Cool.
Yeah. So in this slide that I'll upload, it's wrong. Is it this one? It's just a minute. If R and T describe the pose of the camera, this should be R transpose, not just R. Because you can't have the same rotation twice to give you the original orientation. Does that make sense? Okay, yeah, that's about it. I've completed everything. I've shown you how we go from 3D to 2D. We've learned about the projection, the pinhole model, transformations, rotations, and translations. I ideally think there should be another class on this because this is thank you, Shubodh. Yeah, transformations and rotations and translations. I really haven't covered this. I've just covered the very basics for explaining the camera equation, which was actually the priority. But I don't know. Let's see if we can squeeze in another class on this because this is fairly important. I'll share a document and that document is really nicely written. So if you want to read up on transformations, that's like the go-to thing. It talks about how this frame is just a dot product. It's just a projection, and you can write it as dot products. So it's a really nice thing. And you'll be looking at transformations all throughout. So really just go through that document. Like if you go through one document, go through that transformations document. And yeah, that's the whole thing. If you're given the collection, if it's described in R&T, then your camera coordinates will be written with like this R transpose T and minus R transpose T.
Aryan, I had a doubt.
Yeah.
When you were answering Jivitesh's question, you said X and Y have different focal lengths. They're measured in pixel values. Like, what does that mean?
Okay. Yeah. So look. So your let's say your computer screen itself, it might be something like 2160 into 1080, right?
Yeah.
And let's say you wanna display a square. You wanna display some image on the screen. So it's not like there's going to be a 1:1 correspondence. I will share some numerical examples to there's one over here actually. Just a minute. Okay, actually I'll get back to you with an example, but you can have different focal. You do have different focal lengths in both your X and Y direction.
Very cool.
Yeah. So yeah, that's about it. You guys can leave. If you have any more doubts, you can ask, and I will upload the resources soon. I'll give an assignment on this also. It's not going to be a difficult assignment. It's just some assignment to play around with values, just to get a feel of transformations and stuff. So that'll come out soon too. Do you have any assignments right now?
Yeah, we have a DL assignment, and then I think Udit said he'd give a ROS assignment.
Okay, fine. Yeah, when you have no assignments, I'll just keep in contact with one of you guys and just let me know when you have no assignments. I'll upload the assignments for transformations and stuff. Cool. Any more doubts you can ask? You can leave. Jaydev Sriram asks Casper, is that a doubt? It is my dog. Yes, it is my dog. Where? I will send pictures later. Yeah. All right, guys. I guess you can leave. If you have doubts, you can ask. And that's about it.
Thanks. Bye.
Cool, bye. Srinivas came at the end. Sup, man? Okay, you can stop recording. Shubodh, you can stop recording.